Assalamu alaikum, dear student. Today is the lecture number 3 of week number 5, and the topics we are going to cover in this lecture are the application of Bernoulli equation that we derived in the previous lecture, and the application of Bernoulli equation, the free jet and the confined flow, and the static, stagnation, dynamic and total pressure that we will see what exactly it is in the fluid flow. So let's start the use of Bernoulli equation in case of free jet. So basically what kind of jet we are calling it as a free jet conditions. So one of the oldest equation in fluid mechanics deal with the flow of a liquid from a large reservoir. Okay, in case of large reservoir, as you can see in the picture here, this is a very big reservoir and there is a outlet. You can assume there is a big water tank, okay, or there is a big oil reservoir. Okay, normally if you see in the power plant or in the refineries where they store water, oil and different fluids. Okay, in those areas the tanks are too big, the reservoirs are too big. Okay, and here this jet is called basically the free jet. Free jet means at the outlet of the jet, the pressure is atmospheric pressure and the exit velocity we can calculate. So there are some condition of the free jet condition that you have to remember. So what are the free jet conditions? Consider if this is point 1, okay, and this is point 2, this is point 3, this is point 4 as it is mentioned here, and this is point 5. So in the case of free jet, if the top surface is open to the atmosphere, so the pressure at this point would be atmospheric pressure. So if we are considering it is gauge pressure, the pressure will be equal to 0. Okay, but if it is absolute pressure, so the pressure will not be 0. But if you are considering the pressure at the top surface of the reservoir at point 1 is gauge pressure, so this pressure will be 0. Same at point 2. Same at point 2 and point 4. This is at the exit. Okay, this is at the exit. At these 2 points also the pressure are atmospheric pressure. Okay, so this is the assumption number 2. The pressure at the jet and the pressure at the top of the reservoir will be 0. Now third assumption, at point 1 at the top of the reservoir, since the reservoir is too big, so when the water level or the fluid level will reduce, it will be very hard to observe. The velocity will be very low. Okay, because there is a large surface, big surface, so when the water will or the fluid will come out from a small outlet, the top surface will move very slowly. Okay, so there is a change in position or change in distance with respect to time will be almost negligible. Okay, so in that case the top surface of the reservoir, the velocity at the top surface of the reservoir will be equal to 0. So this is the condition number 3 in the case of free jet. So whenever you are going to solve the problem of free jet, you must remember these assumptions. Okay, so let's see here. So new form for along a streamline between any 2 points. Okay, so this is the streamline, and we applied the Bernoulli equation between these 2 points. So this is the Bernoulli equation we have written in the form of pressure. So if we know point number 5 of 6 variable, we can solve for the last one. Okay, if we know 5 out of 6 variables, we can solve for the last one. Okay, so here for the following, the streamlines between 1 and 2, if you would like to find the velocity at point 2, so you can easily find out. So let's see what is the assumptions or the condition for the free jet. Pressure at P1 will be 0, as I said. The velocity at the top will be 0, so this factor will be 0. Okay, and the point 2 and point 1, so this is our datum. Okay, this is our datum line. So the distance between point 1 and the datum line is h. So this Z1 will be replaced with h. P2, this is the point P2, the pressure is atmospheric pressure, so it is considered to be 0 gauge pressure. Okay, because the gauge pressure I mentioned here. Okay, so same, the velocity at point 2, that we have to find out, or we can find out, that is equal to v. Okay, and this at this point, because the point 2 is at the reference point, so it is equal to 0. If we simplified all this, we will end up with this point here, and finally we can calculate the velocity at the exit. Okay, and this velocity will be equal to 2gh. Okay, so if you want to find out the velocity somewhere away from the exit point, okay, some distance h, so this equation will be end up with h plus h. Okay, so this, in this case, this is the formula that we can use to find out the velocity at the nozzle or at the exit of the reservoir. Okay, so this is the condition of the free jet. Let's see in the second case, free jet, case number 2, horizontal nozzle, smooth corner. Here you can see the nozzle is not at the bottom. Okay, in this case the nozzle is at the horizontal surface. Okay, so we can imagine, we have seen the water tanks, the reservoirs, sometimes we see the discharge at the bottom, and sometimes we see the discharge at the horizontal side. Okay, so here we have a discharge, horizontal discharge, but the exit of the discharge is nicely smooth corners. Okay, in that case, when the water will come out from the nozzle, so it will come with in a very smooth manner. Okay, so whatever is the diameter or the area of the exit or the size of the exit, the jet will have the same size. Okay, so whatever is the diameter of the nozzle, the diameter of the jet will be the same. So in that case, slight variation in velocity due to pressure across outlet. However, we calculate the average velocity because we know the formula. Okay, so this is the height h, and we know that the pressure at this point and the pressure at this point. Here the pressure is bit higher, lower, and here is the pressure is higher. So if we take the if you want to find out the pressure at point 2, you can easily find out. So this will be the average pressure. Okay, because this will minus with this pressure. Okay, so the same formula will be applicable. V is equals to 2gh. or you can apply Bernoulli equation between point 1 and point 2 and you can calculate, and finally you will end up with the same equation. Okay. Now case 3, you can see there is another concept, the horizontal nozzle sharp edge corners. Here you can see the discharge, the nozzle is not as smooth as it was in the previous case. Okay, here the discharge is very sharp. Okay, and in that case what we see, vena contracta, there is another concept. So what is vena contracta? If the exit is not smooth, well contoured nozzle, the diameter of the jet dz will be less than the diameter of hole dh. So this phenomena called a vena contracta effect is as a result of the inability of the fluid to turn the sharp corner 90 degree indicated by the dotted lines in the figure. Okay, here you see this is the sharp edges. Okay, the size, the diameter of the diameter of the hole is bigger, but the diameter of the jet of water is small. So this is dj, the diameter of the jet, and this is the diameter of the hole. Okay, so in that case, here the pressure at point 1, this is the point 1, and the pressure at point 3 is 0, because these 2 points are open to atmosphere. Okay, so that's why here the gauge pressure is 0, and the pressure varies. So the pressure varies and highest at the center point. However, the height of the fluid is very high comparing to the diameter of the jet. So therefore we can write down velocity is equals to under root 2g h. So let's see, there is some correction factor based on the type of the geometry of the nozzle. Okay, if there is a sharp edge, okay, if the nozzle has a sharp edge, this is the diameter of the hole and this is the diameter of the jet. So there is a correction coefficient, there is a correction coefficient, that is cc is equals to 0.61. okay, cc is equal to since it is the geometrical correction, so that's why aj over ah, so dj into dh. So if you want to find out the velocity at the jet, so we can use this relationship. Okay, so if you want to find out the velocity not at the exit of the hole but at the jet, so we can use this correction factor and we can usually find out. So if we have well rounded the correction, we don't need any correction factor, that is equal to 1. So if you have 90 degree corner, the correction factor will be equal to 0.61. If you have the re-entrant, the correction factor will be 0.50. So these correction factor will help us to find out the diameter of the jet and also to find out the velocity of the jet. So now we solve a problem and we see how we apply the Bernoulli equation in the case of free jet. So here water flows from a pressurized tank through 6-inch diameter pipe, exits from a 2-inch diameter nozzle. So this is a pressurized tank. This is not open to atmosphere. Keep in mind, it is closed from the top, but it is a big reservoir. At the top there is a air, and this is the fluid, okay, which is filled with the tank, and this is a 6-inch pipe, and finally there is a nozzle that is equal to 2 inches as shown in the figure. Okay, and rises 20 feet above the nozzle as shown in figure. When we open this nozzle, So due to this pressure, this fluid rises up to 20 feet. Okay. So what we have to do, we have to determine the pressure in the tank if the flow is steady, frictionless and incompressible. Okay. So these are the information given, and we have to find out the pressure due to which the fluid traveled 20 feet distance vertically upward. That we have to find out. So what we can do, first of all we have to assign point 1. This is our point 1. The pressure we have to find out what is the pressure stored here, and this is our point 2, the maximum point. So this we are considering a small streamline. Okay, the one single streamline. Okay, and we are applying Bernoulli equation. So this is the Bernoulli equation between point 1 and point 2. So this is the free jet condition. Okay, this is the free jet boundary condition, or the assumptions that we can see. So this is the velocity, since it is a big reservoir. So velocity at point 1 is 0, and it is a free jet, and also there is a velocity, because here this is the final point. At this point the velocity is 0 2, so V2 is also 0, and this is our reference point. This is our reference point. So this is our reference point. Okay, so at point 1 the height is 0, z1 is from here to here, the z1 is, we can take reference here and we can take reference here as well. If you are taking reference here, so the point 1 is 2 feet away, and if you are and the point 2 is 22 feet away. But if you are taking reference point here, so the point 1 will be, z1 will be 0 and z2 will be 20, and p2 will be 0 because this is the atmospheric pressure. So now we are going to find out the pressure at point 1 P. Now put all the values in the Bernoulli equation. So this we have to find out. Velocity is 0, z1 we know that is z1 could be 0 or p2, or but here we consider 2. p2 is 0 and v2 is 0 and z2 is 20. So now if we multiply it with the density of the fluid, so finally we end up with, this is the pressure which is stored above the fluid. So next move on to the next topic. This is the application Bernoulli equation, another application of Bernoulli equation, the confined flow. So why we need this concept? So see, there are some problems that we cannot solve with the Bernoulli equation alone. So what is this case? There are some flow where we can not know the pressure a priori because the system is confined. So consider this is a system. Okay, this is a system which is confined. We don't know the pressure here, we don't know the velocity here. Okay, we don't know the pressure here, we don't know the velocity here. Okay, we don't know the flow as well. So just like same problem like the fluid passing through the pipe and fluid passing through the nozzles with changing diameters, because here you see the diameter of this nozzle is different, diameter of this tube is different. Okay, in order to address these flows, we consider both conservation of mass, continuity equation, and Bernoulli equation. So here we bring another concept, the conservation of mass. So conservation of mass means mass, once it is entered to the center, enter to the system, the same mass will come out in the same time. So consider flow in and out of a tank. So consider this is a tank. Okay, and this tank is connected with the pipes. Okay, at the inlet of the pipe it has some velocity which is v1, and at the exit of the pipe it has some velocity v2, and the cross section area of this pipe is a1. Okay, because the cross section area, it could be a circle, it could be a rectangle, or it could be a square. Same here, the cross section area of this exit pipe or nozzle is a2. Okay, so the we see with this velocity, with this cross section, the amount of fluid enter to the tank in delta t time will be equal to this much. Okay, and this is the volume entered into the tank in delta time, delta t. Okay, so that means it's covered the distance with the velocity of v1 in delta t time. So that means s is equals to vt, so v into t is basically the distance covered. So this is the distance covered. Okay, this is the distance covered multiplied by the cross section area will give you the total volume entered into the system. Okay, so whatever volume entered into the system, the same volume will come out from the system as well. So here we can see this is the velocity at the exit is v2, and this in the same time delta t, this is the volume which is came out from the tank. So v2 into delta t give you the distance traveled, and the cross section area is a2. So the total, so this is the distance, the cross section area is also the area multiplied by the distance give you the volume. Okay, so if the outlet area is A and the fluid flows across this area normal to the area with an average velocity v, then the volume of the fluid crossing this area in a time interval delta t is va delta t. Okay, because v into delta t, this is the distance traveled, a is the cross section area, equal to that in a volume of length v into delta t. Okay, and the cross section area a. Hence the volume flow rate per unit time is equals to va into q. Okay, here we are not saying volume, here we are saying volume per unit time. Okay, in per unit time the volume will enter, the same volume of fluid will come out from the system in a same time. So what is the volume flow rate would be va is equals to q, and the mass flow rate is equal to m dot is equals to rho v a. Okay, so if you multiply volume flow rate with density, so you will get the mass flow rate. Mass flow rate we calculate in the in SI system in kilogram per second, and in CGS system is lux per second. Okay, so mass flow rate is equals to rho q, and q is equals to va, the volume flow rate. Okay, so we can say that the mass flow entered at point 1 will be equal to mass flow out at point 2. So this is the form of continuity equation, rho 1 a1 v1 is equals to rho 2 a2 v2. So this equation is valid for incompressible fluid as well. Okay, if the fluid is compressible, this equation is valid for both compressible and incompressible fluid. Okay, if the fluid is incompressible, so this equation will be reduced to a1 v1 is equals to a2 v2, then volume flow rate will be equal. Okay, if the fluid is incompressible then the mass flow rate will be equal. Okay, if the fluid is incompressible, then volume flow rate will be equal. So let's solve one example to understand the concept of this confined flow very well. So let's say water flows steadily. Okay, steadily means the steady flow. What is the meaning of steady flow? The meaning of steady flow, the change in velocity with respect to time is 0, and the change in properties also with respect to time is 0. That means there is no change in density, and there is no change in velocity, and there is no change in fluid properties. Okay, the water flows steadily through a large reservoir, through a large tank shown in figure 3.58. So this is the figure. Okay, this is the large reservoir, and from somewhere the water is coming inside the tank, and then it's continued to the, okay, determine the water depth h. So we have to find out this water depth h, and these are the informations given here. So we have to find out this depth h. Okay, so definitely we have to apply a Bernoulli equation to find out this depth h, because the Bernoulli equation covers the depth h. So let's start. We know that the volume flow rate here will be equal to the volume flow rate here will be equal to the volume flow rate here. Okay, so at this point 4, okay, so at this point 4, height is known. At this point the height is known. Okay, here we know the boundary conditions. The atmospheric pressure is 0. Here the atmospheric pressure is 0. Here the velocity is 0. So we can find out the velocity at point 4. Okay, so let's see. So we can say that the whatever is the flow rate here, the same flow rate at point 2 and the same flow rate at point 4. So here Q2 is equals to Q4, where Q4 is equals to A4 V4. Okay, so we cannot find out Q4 unless V4 is known. To find out V4, we applied a Bernoulli equation between point 3 and point 4, and we apply the boundary condition of free jet. Okay, we apply the boundary condition of free jet. So in that case P3 P4 is equals to 0, and V3 is also equals to 0 because it's a large reservoir. So we substitute the value, and finally we get 6.26 meter per second, the V4 velocity. Once we know the velocity, area is known, we can easily find out the volume flow rate. So now it's going to be very simple. Now we know the volume flow rate, so Q2 and Q4 are equal. So here we know the flow. Now it's quite simple, so we can find out the velocity at this point, and once we know the velocity at this point, we will apply the Bernoulli equation. So let's see. We apply the Bernoulli equation between 2 and 1, because at point 1 we know the boundary condition, P1 is equals to 0 and V1 is equals to 0, and V2 we can find out by using this volume flow rate. Okay, so we apply here, this is the boundary condition, and finally we calculated V2, and here by using this we calculated the velocity. We calculated Q4, we know Q4 is known, so we substitute the value here in this equation. Okay, we substitute the value here in this equation, and finally we simplified it, and we get the value of HA is 15.4. so this is quite reasonable question to clear the concept of confined flow as well as the free jet. Now we are going to see another application of the Bernoulli equation to measure the different type of pressure of the fluids: the static pressure, stagnation pressure, dynamic pressure, and total pressure. Let's see what are these pressures. First of all, the static pressure. Basically, the static pressure is the pressure which is due to the molecular collision. Okay, this is the pressure due to the resistance of the molecules. Okay, this is the resistance between the molecule or due to the collision between the molecule. Okay, so we can see the static pressure is the pressure as measured moving with the fluid. Okay, that is static with the fluid. This is the P term in Bernoulli equation. So this is the term basically which indicates the static pressure in the Bernoulli equation. Imagine moving along the fluid with the pressure gauge. So how we can calculate the static pressure? To measure the static pressure, normally we use U-tube manometer or the piezometer. So here you can see we installed a piezometer to measure the static pressure of the fluid. Okay, or to measure the static pressure of the pressurized or moving fluids. Okay, here the static pressure, so here the static pressure at point 1 can be estimated by the height of the column. So this pressure at point 1, it will be equal to the gamma h3 gamma into h from point 1 to 3 and 3 to 4. This is the total height of the column. Okay, so this is from center point to, this is h3 to 1. So this is gamma, the weight density of the fluid into h3-1 and plus the pressure at point 3. The pressure at point 3 is equal to h4 to 3. So this is equal to, so this is the total height into weight density. The weight density got common and total height is equals to h. So the total static pressure will be equal to gamma into h. So this is the way we measure the static pressure. Now the third term in the Bernoulli equation, gamma z, is called the hydrostatic pressure. So this is the term which indicating the hydrostatic pressure. That is, it's the change in pressure due to change in elevation. This is due to the change in elevation. As the depth of the fluid will increase, this pressure will increase. As the depth of the fluid will decrease, the pressure will decrease. Now there is another term, that is half rho v square. This is the half rho v square. This is the dynamic pressure. It is called the dynamic pressure. It is a pressure that occurs when the kinetic energy of the flowing fluid is converted into pressure rise. Okay, so here we basically use a technique to convert the kinetic energy of the fluid into the height of the column of the fluid. To do such thing, to measure the dynamic pressure, we use a device that is called a pitot tube. Pitot tube is basically L-shaped bent tube. This is, you can see, this is a pitot tube. This tube basically do not measure the dynamic pressure directly, it measures the stagnation pressure. Okay, so here at point 2, you can, this is called a stagnation point. Okay, this stagnation point or this pitot tube, what exactly it does, it allows the fluid to enter into the fluid. Okay, so it converts all its kinetic energy into the vertical head or into height of the column. The fluid continues entering into the tube till it has energy. Once the energy is completely converted into the height, once the energy is completely converted into height of the column, the fluid stops entering to the tube. So that's why we consider at point 2 the velocity is 0. So this is the stagnation point. At stagnation point, V2 is 0. So now this is the point 1 and this is point. To find out the pressure at point 2, now we are applying the Bernoulli equation between point 1 and point 2. So this is the Bernoulli equation at point 1 and point 2. So this is at the same frame of same reference line. So Z1 and Z2 is equals to 0, and the pressure at point, this is the point 1. So now apply the boundary condition. At point P1 plus half rho V1 square plus Z1. So Z1 is equals to 0, and at P2 plus half rho V2 square plus Z2. Z2 is 0, V2 is 0, only P2 is remaining. So P2 will be equal to P1 plus half rho V1 square. So you can see here this P2, which is the stagnation pressure, which is equal to static pressure at point 1 plus a factor that is half rho V1 square, that is basically equal to the dynamic pressure. Hence the pressure at the stagnation point is greater than the static pressure P1 by the amount half rho V1 square, the dynamic pressure. So this is the amount of dynamic pressure, and this is the way we measure the dynamic pressure. The sum of the static plus dynamic pressure is called the stagnation pressure, and the sum of the static, dynamic and hydrostatic pressure is called the total pressure. Any sum of the all three component of Bernoulli equation is equal to the total pressure. So there are some more terms for the stagnation pressure or stagnation point. So here you can see when fluid flows around any stationary body. So this is a body, okay. Some of the streamline passes over and some passes under the object. So the streamlines passes like that, okay. But there is always a stagnation point where the stagnation streamlines terminates, okay. So this is the stagnation point where the velocity is 0. This is the stagnation point where the velocity is 0. The stagnation pressure is P stagnation is equals to P, the static pressure, plus half rho V square, where V2 equals to 0. This is the condition for the stagnation pressure. At the stagnation point the velocity is 0. So V is the velocity at some point on a streamline away from obstruction, okay. So this is V, this is away from obstruction somewhere here. So if there are no elevation effect, the stagnation pressure is largest pressure obtaining along the streamlines. All kinetic energy goes into a pressure rise, okay. So we are going to solve example, and we will see how we measure the static pressure, dynamic pressure, stagnation pressure and the total pressure. So here you can see a piezometer. So piezometer is the device that we use to measure the static pressure, and a pitot tube. Pitot tube is the device that we use to measure the stagnation pressure or the dynamic pressure, okay. And also to measure, if you know the dynamic pressure, you can easily calculate the velocity of the fluid, okay. Okay, pitot tube are tapped into a horizontal water pipe. So this is the horizontal water pipe, this is the piezometer tube, and this is the pitot tube, okay. It is always in L shape, okay. And in the across the direction of flow, okay. Okay, figure to measure the static and stagnation pressure for the indicated water column height. Determine the velocity at the center of the pipe. The flow is steady and incompressible. So there is no change in velocity in the fluid. So we have to find out the velocity of the fluid. So velocity of the fluid, definitely it is related to the stagnation pressure. So we know that the stagnation pressure is equal to the static pressure plus the dynamic pressure. So what is the pressure here? So this height of the column will give you the static pressure, and this height of the column will give you the stagnation pressure, okay. So here you can calculate, this is the density of water we know. So rho g H1 will give you the, from here to here, this is H1, and from here to here this is H2. This is 0.1. So from here to here there is a height of the column, that is H, that is 3 centimeter, and here to here H2. So the static pressure P1 is equals to rho g into H1 plus H2. Now the pressure at point 2 is equals to rho g into H1 plus H2 plus H3. So this will give you the pressure at point 2. Okay. So noting that the point 2 is a stagnation point, and thus V2 is equals to 0, and Z1 and Z2. Z1 and Z2 lies in the same reference line. So Z1 and Z2 are equal. So here now the application of the Bernoulli equation between point 1 and point 2, substitute the value of P1, P2, expression give. So this is the Bernoulli equation between the point 1 and point 2. Point 1, this is point 2, and finally we know that at Z1 and Z2 are equal is cancel out. Okay, V2 is 0. So P2 so P2 minus P1 over rho g is equals to V1 square over 2g. Okay, so V1 over 2g is equals to P2 minus P1 over rho g. We simplified that. So P2 we calculated this, P1 we calculated this, over rho g is equals to H3. So here V1 square over 2g is equals to H3. H3 will be equal to, we can see, H3 is equal to 12 centimeter, because this height and this height will cancel each other, only this height will be remaining. So this is V1 is equals to 2 into 9.8 into 0.12. So we converted this centimeter into meter, so divided by 100, this is going to be 0.1 meter. So this is 0.12 meter. Okay, when we simplified it, we got up 1.53 meter per second. Note that to determine the flow velocity, all we need is to measure the height of the excess fluid column in the pitot tube. That's all for the